All right, so the purpose of today's lab is that we want to be able to work on our position versus time and y equals mx plus b skills, okay? So normally what I do is I have everybody go into the atrium together and we're running carts down the atrium hallway and we're measuring and stuff like that. But with COVID, that's way too many people like really close together handling all the same stuff, and there's a way to avoid it, so we're going to avoid doing it that way, okay? And what I'm going to do is show you how the data is going to be gathered so that you can see where all the sources of error are going to be, okay? And then I have incredibly awesome data that I acquired myself, okay? That's going to make perfect graphs for you, right? And what that'll do is save us a whole bunch of time as well. Okay, it keeps us safe from COVID, but it also saves us a whole bunch of time because you're not going to have to take all the data, fix it all up, and then get it ready. It's all ready for you, and you should be able to get like the vast majority of this lab report done in class today and not have very much homework. All right, so it's going to save you guys a bit of time later. All right, so what we're looking at as our problem is we're trying to figure out what the relationship between distance and time of an object traveling at a constant speed is. Okay? Now, the fact that we have kind of seen this already on a number of other graphs, and we know that a position versus time graph of an object traveling at a constant velocity looks like this, okay? We already kind of know what the relationship is. As time increases, so will what? The distance traveled, or the position will continue to change. The speed is going to stay constant. I'll repeat that. The speed or velocity is going to remain constant. That is, it isn't going to change at all at any point by anyone throughout the lab. That's clear enough, right? We got that one? Okay. We want that to stay the same. We want it to stay the same because we're trying to figure out what's the relationship between position and time. Now, the way that's going to work is that we're going to allow these carts to travel, and we're going to determine when they start and when they stop in terms of time. That is, we as the experimenter are determining the length of time over which the cart will run. And the longer we allow it to run, the farther it will go. So I kind of gave you most of the variables there. And you need two more controlled. In case you're wondering, I've given you the manipulated, responding, and one controlled at this point. Okay? So the other controlled variables are kind of things that you're going to see as I show you what the experiment looks like, okay, as the experiment runs. Right? Obviously, the whole experiment is going to be contained within this room, so you're looking at maybe some conditional stuff as controlled variables, okay, within the room, or maybe some procedural stuff as you watch me show you what the lab would look like. Okay, now for our hypothesis, okay, what we're looking for here, okay, in the if part, okay, is for you to talk about what happens to position, okay, for a cart traveling at a constant velocity. So if a cart traveling at a constant velocity, or if position does this as a cart travels at a constant velocity, that's what the if part needs to talk about. Okay, what's going to happen? Okay, what's the relationship? Is position going to go up? Is position going to go down? Is position going to remain the same? Okay, that's what you got to talk about in the if part. Okay, the and part, okay, is simply that 5 carts are going to have their position and time data graph. I better be a little more clear about the if part. I just was listening to myself in my head, and it sounded awful the way I described that, so I'm going to say it a different way. Okay, so in the if part, okay, start it like with this. if position, and then tell me what it does as a cart travels at a constant velocity, okay? So tell me if position either goes up, goes down, whatever, okay, kind of fill in the blank here, as a cart travels at a constant velocity, and 5 carts, graph, then, in the then part, how will you calculate velocity from your position versus time graph? That's what you need to tell me in your then part. Okay, so then velocity can be calculated by doing this, but it has to be using your graph. Okay, what I don't want to see is this. Oh, we'll just use v equals d over t. No, we won't. Okay, I don't need to go through the bother of building a graph if I'm just going to do it that way. Okay, using a graph is more accurate because if I use this, I'm just using the first point and the last point, and I'm ignoring all the other data points that I got throughout the lab. Okay, well then what was the point? All I could have done was just watch the cart go, mark its starting point, mark its ending point, and be done, and use v equals d over t. That's not the point. Okay, so I want you to tell me, how can you get velocity from your graph? Okay, everyone follow me there. Okay, there's a little something about the graph that will tell us that. Okay, we've done it before. All right, questions so far? Okay. So I've included an observations video with this, but I'm going to kind of show you guys what that looked like. Okay, so like I say, we used to do this a much less accurate way, which was that we would just let these carts run down the atrium along a measuring tape, and every 5 seconds somebody would put a mark on the measuring tape, marking where the cart was. How much error do you suppose that had? A lot of error. Okay? Now, we still got position versus time graphs that were usable, and we could do all of that, but it took a lot longer and wasn't nearly as accurate. So, last year, we got these data gathering carts, which have a little sensor in them. They communicate via Bluetooth with your phone, and they transmit the data 20 times per second instead of once every 5 seconds, 20 times per second about the position, the velocity, and all that of the cart. So all we did is rigged up a hitch. That's a hitch. Okay, it's a red-green hitch, except I didn't have duct tape. Okay, it works. And it makes sure that the cart pulls, the motorized cart pulls the passive cart along with it very, very easily. Okay, it doesn't slip, okay, and it doesn't bounce around. We tried it with a string, but inevitably what happens is the cart would pull, and then the string would yank the cart, and it would run into the back of the cart, and it would just bounce around the whole time and get really crappy data. So we did that the first time, realized how many sources of error they were, and fixed them all. Now they're fixed. This is it. Okay. So what we do is we simply put the cart, okay, on the floor like this, and we make sure it's connected to my phone so that it can gather the data. So kind of watch now, see if you can find any sources of error that I might have as we go along here. Still have the data from the last one. Okay, so now I'm connected to this cart, okay, and I've got this app open on my phone. It's nothing special, it's just going to show the data, it's going to collect it, and I'll send it to myself. Okay, so I'm just going to get a graph ready here so I can see what's going to happen, okay, with this cart. And then, because there was only one of me, okay, I'm going to set the phone on the floor, okay, I'm going to fire up the cart, and I'm going to hold it, start my data, and then let the cart go. the data that you've got. So anyway, that's what it looks like when I collect it. I'm not actually going to use this data because I've already collected 5 runs worth of perfect data for you. Okay.
For whatever reason, it was not. Oh, I know why.
Okay, here, you want to see, this is like about as smart, what I just did. About as smart as that guy that strapped down the load on his truck through the wheels. You ever seen that meme? Where all the cargo straps, everything is strapped down, and he ran the straps through the spokes on the wheels of his truck. So that as soon as, of course, the truck started moving, the straps would break. Look where I put the tape. This thing doesn't record data unless the wheels spin. It's Monday, and I haven't had my coffee yet. I was really careful about this one. I just didn't notice the front one. Okay, so anyway, I didn't do it that way when I collected the data, because I was, well stimulated with caffeine and Monday. Okay, all right, so that's how the data was collected, and then I just did that 5 different times with 5 different battery-operated carts, all of which traveled at a slightly different velocity because, well, I found really brand new batteries and like slightly dead batteries and a little more dead, just so they all went different speeds. That's not the manipulated variable, okay? I already gave you the manipulated variable because I determined how long the carts would travel for, and then I measured their position as a function of that. Okay, so that's the experiment, okay? And you can see that it was run on this floor, okay? Drag the carts over exactly the same path. I actually kept them on the middle tile, middle row of tiles here, each and every time. Okay, so that I could kind of keep everything that might affect the speed of the cart the same. Okay, everybody with me there? All right, so the next thing we got to do is we've got to build our graph. So in case anyone's forgotten, I'm going to quickly walk through the graph building, okay, with Google Sheets. So you're going to need this data right here. All right, so if you open that up, this is what you'll see, right? And I was taking data 20 times per second, okay? For some of these, for the longest one, it was 20 seconds, right? For the shortest ones, it only ran for about 10.9 or whatever, but still. Okay, it's more than enough data to make this work. So, okay, so this is where I'm going to stop. I'm going to stop at 10.9 seconds, and I suggest that you all do the same. That way, all of our graphs end at the same point in time. Okay, and that's kind of a fair comparison then. All right, so you can see they all definitely did travel different distances. These two are pretty close. Okay, so cart, what would it be, 2 and 3? Okay, we're pretty close to the same speed, but the other carts are noticeably different. Right, so once I've got all that highlighted down to 10.9 seconds, I'm going to, oh, I'm in view only, sorry, you guys have to, okay, so here's what everybody has to do, sorry. You need to make a copy of this data for yourself. Okay, so just click make a copy. Because you'll need to be able to edit it, and I didn't give you editing privileges on the first file. Okay, so now you're going to be in the one that says copy of, okay, and you're going to highlight down to 10.9 seconds again. Like so. Everybody there? Okay, insert, chart. Okay, same as we did before. All right, and of course Google Sheets picks a terrible, terrible choice, so we need to go to column chart here. Then you need to scroll down to make it a scatter plot. Okay, so that's right here. So you'll have to scroll down until you get the scatter plot. what we see is this. Now you can see it's made all the points really big. So they overlap so much because there's 20 of them every second that it actually already looks like a solid best fit line because the data is so awesome. I'm not bragging, it actually really is. That's straight. Okay, so now what you want to do is go to customize. Okay, because this graph needs some stuff. It needs a title, okay? It needs labels on the axes. Okay, so remember you go chart title here, and you can go chart race, whatever you want to call it. Chart race, whoa, it's moving. Chart race, and it's still on caps. Position versus time. Okay, and then obviously put on your horizontal axis titles. Okay, that's going to be time in seconds. Okay. And your vertical axis title, that's going to be position meters. Okay. And then go to series. And I would suggest, like it says here, apply this to all series. So at this point, what you want to do is probably change all those points down to smaller dots. They're still going to overlap just because of the way we did it. Okay, and then you want to go down to trend line. Click on that. Okay, and then here on label, you want to get the equation. Same as what we did when we were practicing doing this last week. Alright, so now we've got, okay, y equals 0.08x plus this. Okay, we've got the y equals mx plus b for each one of our carts. Okay, so there's, now we can kind of do the analysis that we need to do now that we have that built. The other thing you might want to do is, since these are all circles, rather than click apply to all series, okay, what I did is I changed like the shapes. Not that it makes a big difference, you can't really tell, I think, but you can tell a little bit at least. And I just changed the shape for each one. It makes a little bit of a difference, at least you can see something on those lines.
So we should do that?
It's up to you. I just did it just because it changes the like it makes the lines appear, or the points appear a bit fuzzier, so that they're obviously not your best fit line. Because as you can see, you can't see your best fit line. Okay, the points are all so close together that the lines actually don't show up because they're so linear. Okay, but you do have the equation for each line here on your legend. Okay, so once you've got the graph looking like you want it, okay, you can close the chart editor, click on the 3 dots. Copy the chart and bring it over to your Google Doc. Okay, so hopefully you guys have more written than I do. Copy and paste your Google Sheets table and graphs here. You don't need to include your Google Sheets table because I gave it to you. Okay, so I already know what the data is. So on this one you don't have to do that. Paste it in there, and you want to paste it linked. That way, if you go back and make any changes, they automatically change in your lab. You don't have to recopy. Okay? Okay. My graph's in there, and now I can move on to the analysis. Okay, so in the analysis, okay, for question number 1, show how you would calculate the slope of each car's line on the graph. So, what I want you to show here is each one of these equations manipulated for slope. Okay, so that means that they're going to still have y and x. Don't put numbers in for y and x. Leave them as letters. Okay, you don't know what they are. X is still in this equation right here. Okay, y should be out here. It should say y equals 0.292 times x plus this number. Okay, I want to see that equation for each car manipulated for slope. Okay, do not put numbers in for y or x. I just want the equations manipulated, so it's the slope equals, and then whatever.
So we don't
Okay.
solve it
Nope,
then?
well,
Okay.
it's kind of already solved,
Yeah,
right? Slope's already in there, in that equation, okay? Google Sheets spit that out. So I just want you to show so that it's solving for that. So it'll say whatever number is the slope equals y, blah, 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 okay, on the other side. Okay, and then for questions 2 and 3, you're manipulating, you're using the equations, okay? And you're solving for either a y value or an x value. So in number 2, it says using the equations for each car, calculate how far each car would travel in 150 seconds, show your work. So what I want to see there is part 1, and I want to see the equation manipulated, okay? And then the answer that you get, remember to put units on. Okay, same thing for question number 3. Show me the equation for each car manipulated to solve for how long it would take, okay, to go 100 meters. Show me the answer with units. All right, so nothing we haven't done before. Okay, we've done a whole bunch of calculations like that already. Okay, so that's what you're doing for the analysis. Then for your conclusion, does your graph fit? Were you able to calculate the velocity? Okay. And what represented the velocity, okay, if it's on there, okay, and then your sources of error, 2 of them, ways to fix them, and you don't have to do the class discussion. We will talk about those when I hand back the lab reports. Okay, any questions? All right, have at her. If there are questions while you're working, just